Now that we have done an example modeling a spring mass system, let's look at our differential equation with the parameters m greater than 0, gamma bigger than or equal to 0, and k greater than 0, where our differential equation is m times u double prime plus gamma times u prime plus k times u equals 0. As we did in the example, we can solve this by looking at the characteristic equation m times r squared plus gamma times r plus k equals 0. And we can find the roots using the quadratic formula. We'll have that the roots r1 and r2 are given by negative gamma plus or minus the square root of gamma squared minus 4mk all over 2m. And we saw when studying second order differential equations that the solutions will depend on whether we have two real roots, a repeated root, or complex roots. The case that we're in will be determined by the discriminant gamma squared minus 4mk. In particular, whether the discriminant is positive, 0, or negative will determine if the solutions are two real roots, one repeated root, or complex roots, respectively. Let's look at each of these cases individually. In case 1, where gamma squared minus 4mk is positive, the general solution is given by u equals c1 e to the r1t plus c2 e to the r2t, since the roots r1 and r2 will be distinct real values. But we can find out more about r1 and r2. Since m and k are both positive, we have that gamma squared minus 4mk must be less than gamma squared. And thus the square root of gamma squared minus 4mk must be less than gamma. From here, we can conclude that the numerator, negative gamma plus or minus the square root of gamma squared minus 4mk, must be less than 0. And thus both roots r1 and r2 are negative, because dividing by 2m won't change the sign. And notice here that since r1 and r2 are negative, the solution u equals c1 e to the r1t plus c2 e to the r2t will go to 0 as t goes to infinity, since our coefficient of t in both exponents of our exponentials are negative. Since the solution does not lead to the mass oscillating up and down, as these exponential functions are not periodic, we call this system overdamped, because the spring almost immediately comes to rest because the damping is so high. The second case that we'll look at is when gamma squared minus 4mk is negative. Here we'll have complex roots, and the general solution is given by u equals c1 e to the negative gamma over 2mt times sine of mu t plus c2 e to the negative gamma over 2mt times cosine mu t, where mu is given by the square root of 4mk minus gamma squared over 2m is the imaginary part of the roots. The real part of the root, negative gamma over 2m, is the part that is not under the square root. Now, if gamma is strictly positive, then we have that this real part, negative gamma over 2m, is strictly negative. From here, we can conclude that e to the negative gamma over 2mt goes to 0 as t goes to infinity. And thus the solution u equals c1 e to the negative gamma over 2mt sine mu t plus c2 e to the negative gamma over 2mt cosine mu t goes to 0 as t goes to infinity. As in the first case, the mass eventually comes to rest, because the position u eventually goes to 0, at least very close to it. The difference here is that sine and cosine cause the solution to oscillate up and down with a smaller and smaller amplitude, as we would expect from a mass on a spring. We call this system underdamped. I want to note that if gamma equals 0 and there is no damping, then e to the negative 2mt is equal to 1, and the mass will oscillate forever. The damping is what causes the mass to come to rest. In our last case, where gamma squared minus 4mk equals 0, we have the repeated root negative gamma over 2m, and thus the general solution is given by u equals c1 e to the negative gamma over 2mt plus c2t e to the negative gamma over 2mt. As in the overdamped case, both terms tend towards 0 as t goes to infinity. We call this system critically damped. I want to point out that while we have 3 separate cases of what can happen, in all of the cases where there is damping, i.e. gamma is positive, the solution to the homogeneous differential equation tends towards its rest position u of t equals 0 as t goes to infinity.